Today we will discuss BCS theory. BCS theory was given by three scientists, Bardeen, Cooper and Schrieffer in 1957. And for this discovery, they were awarded Nobel Prize in 1972. This theory is based on advanced quantum concepts and mathematical techniques. This theory basically explains the behavior of low TC superconductors. Here we'll discuss important aspects of the BCS theory in qualitative manner. BCS theory describes the superconductivity as a microscopic effect caused by the condensation of Cooper pairs. Superelectrons, that is Cooper pairs, have bosonic properties. In the normal state of a metal, electrons move independently, where BCS theory states that they are bound into Cooper pairs by an attractive interaction. We know that electron is a particle which follows Fermi-Dirac statistics, obeys Pauli's exclusion principle, having half integer 1 by 2, 3 by 2, 5 by 2 and so on. Whereas bosons do not obey Pauli's exclusion principle and have integer values of spins 0, 1, 2 and so on. When boson particles are cooled down to very low temperature, or in other words we can say that close to absolute zero, then the kinetic energy of particle decreases to a negligible amount, so that they condense into the lowest energy state. This property is used for the explanation of superconductivity. So bosons at sufficiently low temperature form large Bose-Einstein condensate. Earlier, electron-phonon-electron interaction was suggested by Pauli in 1950, but could not explain the behavior of superconductors. Later, Bardeen, Cooper and Schrieffer suggested that phenomena of superconductivity occurs because system in superconducting state has lower energy than in normal state. And mechanism for this energy lowering can be explained on the basis of three basic ideas: electron-electron interaction through phonons, formation of Cooper pairs, and existence of an energy gap. So we'll discuss all these phenomena one by one. So first we'll discuss electron-electron interaction through phonon. As we all know that there is a Coulomb repulsion between two electrons. But BCS theory says that an attractive interaction takes place between two electrons. So we'll see how this attractive interaction takes place. For that, we consider a crystal lattice that is site of positive charges. So all these red circles are the positive ions, and all positive ions in a lattice are connected elastically. Positive ions vibrate about their mean position. If an electron enters into this lattice, then what will happen? Positive ions will be displaced and bonds will be distorted or disturbed. So when electron enters in this region, so bonds near these electrons will be distorted because an attractive interaction takes place between these positive charges and electron. So electron suffers an attractive interaction. So there is a region of high positive charge density is produced due to deformation, which is also known as phonon. Suppose this electron reaches to this region, then high positive charge density region will observe here. Now, if second electron moves into the region of high positive charge density, then as this electron enters into lattice, we see that bonds are disturbed. But as this electron reaches to this high positive charge density region, then interaction between second electron and distorted lattice occurs. Like this, interaction between second electron and this distorted lattice occurs, which is the site of high positive charge density region. So in other words, we can say that there is an interaction between electron and electron through phonon, and attractive forces are greater than the repulsive forces. This results in lowering of the energy, which implies that force between two electrons is attractive. So two electrons are then effectively coupled together and become correlated. The displacement or deformation or distortion of positive ions depend on mass. How this depends on mass? Let us see. If we consider two objects, M1 and M2, if M1 is greater than M2 and same force is applied, then displacement will be different. Suppose this is M1, this is M2. Mass of M1 is greater than M2. If the same force F is applied to both, then M1 will displace less as its mass is higher, and M2 will be displaced more. So we can say that if mass of the positive ion is more, then distortion will be less. We know that energy of the phonon is related to its mass, as EP is directly proportional to 1 upon under root m. So smaller the mass of the ion, greater will be the deformation. Hence, larger Tc will be required to break the electron pair. Larger Tc means more energy will be required to break the electron pair, and vice versa. If mass of the ion is larger, then smaller will be the deformation and smaller Tc will be required to break the electron pair. If you remember, the same conclusion is drawn from isotope effect. That isotope effect states that if critical or transition temperature increases, then its isotopic mass decreases. So isotope effect was able to explain that lattice vibrations are involved in explaining the phenomena of superconductivity, but how these lattice vibrations are involved, that could not be explained by isotope effect, which was explained successfully in BCS theory, that how how electron-electron interaction through phonon takes place, how an attractive interaction between two electrons through phonon field or through lattice deformation takes place. So in the next lecture, we will discuss formation of Cooper pairs.